Hello guys, welcome back to our lectures. In this video we're gonna explore the ALU design, MIPS ALU design, how to design in hardware a MIPS ALU. So first, before we go into the details of that, we should know the basic building blocks we're gonna use to build that ALU. So basically it's a bunch of gates and modules. So the first gate is the AND gate. So if we have inputs here A and B, the output is A and B. Okay. Then we have the OR gate. So the output is OR here. Then we have the inverter or the NOT gate. And if A input here, then this will be A inverter. We are also using what's called MUX, multiplexer. So the multiplexer is actually, has 3 inputs, like A, B, and C. Or let's call it S for a moment, So this input is special input. It's basically based on the signal S, either A or B will be reflected in the output here. So for example, if S equal to 0, the output will be A. If S equal to 1, the output will be B. Okay? And we might have a bigger multiplexer like this, for example. This is 2 by 1 multiplexer, this is 4 by 1 multiplexer. So the selection now should be 2 bits. Like for example 0 0. So let's say A, B, C, D. In that case A will go out, or the output will be equal to A. If the selection is 0 1, the output will be B. If the selection is 1 0, the output will be C. If the selection is 1 1, the output will be D. Okay? Finally, we should have the adder. The adder is another circuit which is just a combination of AND and OR circuits. Okay, so basically it has 3 inputs, A, B, and C, which is what's called the carry input, and it will give you what's called the sum bit and a carry bit. Like for example, let's add 1 1 1. So A here is equal to 1, B is equal to 1, and the carry input is equal to 1. Okay, basically this is 3. So 1 plus 1 plus 1 is 3. 3 means you have a sum of 1 and a carry of 1. So the output will be 1 1 as you see here. Okay, these are the basic building blocks. If you need to understand more, just review my videos and course in VHDL design or digital design, and you're gonna have much more details on how to design all such building blocks. Okay, first the simple 1-bit ALU design. So this is the circuit shown here is the basic building block for any MIPS, or even any other processor. So let's see here. This basic building block can do actually 3 operations. Okay, let's assume that A and B are just 1 bits. Okay, so if you want to do AND, you should here put the operation equal to 0. So the output here will be equal to A and B. If the operation equal to 0. If the operation is equal to 1, then the output will be A or B. Remember this gate here, the OR gate here, has 2 inputs, A and B. Or let's write it A OR, just to be, because we have then the addition. So with the addition, there be some confusion between the signs. So this is A and B, A or B, and finally if the operation or the the selection is equal to 2, this will be A plus B. Okay, and there will be a carry also in that case when the operation is equal to 2. Okay, now I'm saying that A and B is just 1 bit. How about if we have 32 bits? Then you should repeat that 32 times. So basically the the A, the register A, for example, is basically A31, A30, A29 until A3, A2, A1 is 0, 32 bits. And B is the same. B is equal to B31, B30, B29 until B3, B2, B1, B0. Again 32 bits. Okay? So each one of those is basically the circuit of the previous slide, which was look like this. Here is the result. This is 0, this is 1, this is 2. And this is the carry out, or let's call it C out here. And here is C in, and here is A, and here is B. Okay, so we just repeat that unit into all these units. So the first unit, for example, will take A0 and B0. The second unit will take A1, B1, and so on until A31 and B31. And now this carry out is now clear where it's going. So this is C0. This is basically C1 until C30 here. Okay. So the carry will be carried into an input to the second and third and so on, ALU 1-bit units. Okay. How about the carry in here? The very first bit, this should be 0. If you are adding, like for example 1 0 plus 1 1, if you adding these two numbers, you can say that there is an input carry, which is 0. So 0 plus 0 is 0, 0 plus 1 is 1. Then, and we have a carry of 0, so the first carry here will be 0 after the first operation of the first bit. Then 0 plus 1 is 1, 1 plus 1 will be 0, and we have a carry of 1. Okay, so in that case here, this is 0, this is 1, this is 1, this is 1. This is the carry input is 0. The first resulted carry will be 0. The second resulted carry will be 1, and so on. This is just for 2 bits. Good. Now, how to do subtraction? In subtraction, we said that A minus B, okay, this can be converted into that way: A plus B bar plus 1, because B bar plus 1 is actually minus B. Okay, this is basically the 2's complement. So we must upgrade our 1-bit ALU to make, or to allow us to use the inverted version of B. And we must have inverter to do that. So in that case here, we're gonna have this inverter and this multiplexer here. So, and we're gonna have a selection input to tell us whether to use B inverted or not. So if you are doing A plus B, for example, the operation should be 2. Okay, and so here the operation will be 2, and the B invert will be 0. So this selection here will be 0, so the output here will be B, or B small because it is 1 bit. If we are doing subtraction A minus B, still we're gonna use this adder, which is corresponding to operation of 2, but we're gonna make the B invert 1. So if this is 1, this will be B complement or B inverted. And the carry input in that case will be 1. So here let's write it. So CI, let's repeat this from the beginning, that's fine. So if you are doing A plus B, the operation is 2, as we said before in the previous slide. We don't need the B invert, so we're gonna put 0. And we're gonna put the carry input equal to 0. If you are using or you wanna make A minus B, in that case, is still the opcode is or the operation is 2, because we are using also the same adder here circuit. But now we want B inversion plus 1. So the carry input must be 1 in that case, and the B invert should be 1 as well. So here it will be 1, so the output will be B complement. So we learn something here. We learn that the operation code or the selection code basically in the bigger mux here for the addition and subtraction is the same, but we added another input to differentiate between the two operations, the addition and subtraction. Let's upgrade one more. How to do NOR, how to do NAND, using still the same foundation. So what is NOR? NOR is basically A or B complement, or not A or B, that's fine. This is not. Okay? So there is a theory called De Morgan's theory or theorem, in which you can like distribute the inversion into the A and B and the OR operation here. So this will be equal to A inversion and B or B A invert or A complement dot or let's write it and that's better. And B complement. So now we need A invert. So we're gonna add another input here called the A invert. And to do this NOR, we should put, so NOR here, we should put the operation equal to 0. I'm sorry, equal to 1, equal to 0, yes, because we're gonna do ANDing at the same. We're gonna do ANDing. So the operation will be 0. But we're gonna put A inv and B inv both ones. How about NAND? NAND is basically A and B complement, or the inversion or not A and B. Again, using De Morgan's theorem, this will be A complement or not A or not B. So again, we're gonna use the same OR that we have before with the same operation code. So for NAND, the operation code will be 1. But again, we need A inv and B inv. So A inv will be 1, B inv will be 1. Just to make it clear for you, what if I want to make OR, the normal OR, which is A or B? what's gonna happen? So for OR, the operation is 1, but the ANV and BNV are just zeros. How about NAND? For NAND, I'm sorry, how about AND, not NAND? I wanted to discriminate between the AND NAND and the OR NOR. For the AND, so we're gonna use 0 here, and ANV, BNV are just zeros. Okay, that's basically how we upgrade to include NOR and NAND. Now let's upgrade a little bit more and include the functionality of set less than. Set less than. That was an instruction in MIPS. So let's remember this instruction, set less than CAB. So C will be equal to 1 if A is less than B. Otherwise, C will be equal to 0. So what we want to do here is basically the result here, which is 32 bits, should be if A is less than B, or let's write now capital A, less than B. This result, which is 32, should be like this, 0, 0, 0 until, 32. So you have 31 zeros, and only the bit 0 is equal to 1. Okay, only bit 0 equal to 1. Bit 0 equal to 1. Otherwise, the result should be like this, all zeros. 32 zeros. So what we're gonna do is basically to subtract A minus B, because we already can do subtraction. We already can do the subtraction. But in our subtraction, we know that if the output is negative, that means A less than B, and that's what we care about. We don't care about how exactly if A is 7 and B is 9, the output will be minus 2. We don't care about the 2, we just care about the minus. And the minus will be our indication that really A less than B. And where is the minus should appear? Basically, if the output most significant bit is 1, that means it's 2's complement, it's of some sort of number, and it will be negative. So if the output of the last bit, the last ALU unit, number 32, or this one here, if we started from 0, it will be 31, will be equal to 1, that means it's a negative, and really A less than B. So what we're gonna do is the following. We're gonna take the output of the last bit. This is basically ALU unit 31, this one here. Okay, we're gonna take the output and we'll call it set. So, and we're gonna set or connect this set input here to all other to the very first ALU unit, ALU 0. So we're gonna add another input. We're gonna call it less. It means less than. And the very first less input is basically equal to set, which will be 1 if A is less than B. We said that in case A less than B, we want all the outputs to be 0 except the very first one. That's why we connected the set to the less input of the very first bit, which is basically that one here. The very first bit, the least significant bit is basically ALU 0. And the same less input for any other ALU unit, is including the last one, will be connected to 0. So if really A less than B, what's gonna happen is the following. We should see that result is 0 or bit 0 is 1, then 0, 0 until also 0 at the last bit. Okay? Why is that? Because we don't care about the value of the negation or the subtraction. We really care about only the sign. So we're gonna take the sign and equate it or assign it to the very first bit. So the output will be all zeros except the first one, basically equal to 1. This is equal to 1 here. Another instruction is branch equal. Branch if equal. So we are saying that jump if A equal to B. A equal to B, that means that A minus B should be 0. Again, we're gonna use a subtraction. So for example, 1 0 minus 1 0 is basically 0 0. So all bits in the result should be 0. So what's gonna happen here is that we're gonna take all the result outputs and OR them together. So if all of them are zeros, so the output here will be 0. That means they are all equal. But we really like the idea that all of them are ones. So we're gonna put the inverter and and we see 1 here. So we see 1 if A equal to B. Also they call this output 0 output. But this 0 output will be 1 if A equal to B. It's confusing, I know. So the 0 output will be 1 if A equal to B. Finally, how we can detect overflow. So overflow happens if in two cases or under two conditions. For an overflow to happen. First, A and B should have the same sign. Same sign means that A31 should be equal to B31. If they are positive number, these two bits should be zeros. If they are negative numbers, these two bits should be ones. This is condition 1. The second condition, the output has different sign from the input. So the output or the result has different sign from the inputs, from either A or B, because we are agree that the first condition means both have the same sign. Let's have an example. Let's see some example. Let's add 1 0 plus 1 0. What is this? Basically, before doing anything, what is this 1 0 plus 1 0? This is not 2. This doesn't equal to 2. Because this is basically a signed number and the most significant bit is 1. Let's assume that the number is 2 bits here, 2 bits. So that means it's a 2's complement. So we should convert it back to its original form. Let's do the first the addition, then we should look at the original form on the original number. 0 plus 0 is 0. And we have a carry of 0. Then 0 plus 1 is 1. 1 plus 1 is 0. And we have a carry of 1. So that's an overflow. How we could detect this? Basically, the two inputs have the same sign because basically both have the same ones at the most significant bit, and the output has different sign. One may say, but we should put the 1 here. No, because I'm saying this is 2 bit, so I'm assuming the register is 2 bit. Okay. Now what is this basically? So this number here is if we wanna make it, if we wanna convert it to its original shape, we should convert it to 2's complement. This will be 0 1 plus 1. This is basically 1 plus 1 is 0. We have a carry of 1. This is 1 0. This is basically minus. This is basically minus 2. Yes, minus 2. Okay, this is basically minus 2. So, and of course, minus 2 minus 2 is minus 4. And minus 4 is not 0 0, of course. To represent minus 4, we need more than 2 bits. Let's do it. So 4 is 1 0 0. This is 1 1 0. We add 1. 0, we have a carry of 1. 0, we have a carry of 1. So this is basically, so minus 4 should be written like this, 1 0 0. Okay. So the two conditions are, again, A and B should have the same sign. That means the most significant bit, which is in 32-bit registers in MIPS, is A31 and B31, should be equal, either 0s or 1s. And the output has different sign from the input. That's basically the case here to show it. So 0 1 plus 0 1 should be 1 0 0, which is minus 4. But the output here was just 0 0. So how to do this? How to design basically this overflow detection circuit? So what we're gonna do is the following. We're gonna express first or represent first this condition. So we should check if this is A30, if A here is equal basically to A31 and B here is equal to B31. So we want to check if they are equal in sign. So basically this is a NOR, this is XNOR circuit. So A, B, XOR 0 0 0 1 1 0 1 1. XOR, which has this symbol, will be 1 if they are different, will be 0 if they are the same. So 0 here, and here they are different. So XNOR is the opposite. So XNOR now which is like this. It's just the inverter of XOR. So it will be 1 if they are similar. So we need first an XNOR like this, and we're gonna connect A and B to that XNOR. So this XNOR will produce 1 if A equal to B, which is have the same sign, I mean, which is the first condition. The second condition, the output has different sign from either A or B, because basically A and B should have the same sign. So we need XOR, and we need either A or B. Let's use, for example, A. You can use B, it's okay. And here is the output, the result. The last bit. So this is basically result 31. If this is A31, this is B31, this is result 31. Bit 31 of the result. So if this is 1 and this is 1, that means that the two conditions are satisfied and we have overflow. So we should do AND gate here because this is the overflow. So simply we can draw it nicely here. Here, for example, A31, B31, and then we have XOR that take as input, let's say B31 and result 31, and then AND gate and here is the overflow. This output overflow will be 1 if you have two ones here. That means A and B have the same result, but the result itself, I'm sorry, A and B have the same most significant bit, the same sign, and the result is basically have different sign from the two inputs, either A or B. Finally, let's now explore the opcodes of all these operations together. Okay? Of course, we have 3 inputs for this ALU unit. This is now the symbol for a 32-bit ALU unit. Okay? It has 2 inputs, A capital, B capital. Let's name them A capital, B capital. It has also 2 other inputs, which is A invert and B invert. And remember, the opcode or the operation is 2 bits. So let's say the AND is 0, 0. When we do AND gate, we don't need A invert or B invert, or not. We don't need not A or not B. The OR should have a different opcode like 0, 1, and we don't need not A, we don't need not B. The ADD operation should have different opcode like 1, 0. Again, we don't need B complement or A complement, or we don't need not A, we don't need not B. Subtraction. Oh, subtraction will use the same adder as the addition, so it has the same opcode. But the difference is that B should be negated, B should be inverted. We should use not B. But A is the same, we don't need not A. NOR is like an AND, but with 2 inputs, which is B complement, A complement. NAND is like an OR, same opcode of OR, but again we use B complement and A complement. Set less than need a different opcode, which is 1, 1. If we go back here, one slide, 3 is 1, 1. And for the slide less than, we need B complement. We don't need not A or A complement. Why is that? Because in slide less than we do A minus B. Remember this. For branch equal, again it's a subtraction operation, so we need B complement. We don't need not A, and actually it doesn't have to have opcode. Don't cares. But we can use just the opcode for for set less than, because it's basically different out there. So basically we are saying here that when you use or when you do set less than and the branch equal, actually the hardware itself is exactly the same. Also for branch equal, we gonna care about the final the final output of the OR gate, the 0 output. So we're gonna look at the 0 output in that case for the branch equal. Okay guys, that was it for the ALU operations and the implementation in MIPS. Thank you very much for watching, and see you in the next video. Bye bye.